Empecemos entonces. Pues voy a leer para no omitir nada. Good morning, everyone. It's a great pleasure to welcome you to this 5th edition of the workshop on statistical physics. On behalf of the organizing committee, I would like to thank all of you for being here today. We are particularly grateful to the 3 professors who will deliver the tutorial courses, as well as our invited speakers for accepting our invitation and for sharing their work with us. This workshop brings together researchers working on different aspects of statistical physics and complex systems. Our goal is to create a space for discussion, exchange of ideas, and potential collaborations. We have prepared a program that combines a variety of perspectives from theoretical developments to applications of statistical physics. We hope this will stimulate interesting discussions throughout the event. We encourage you to actively participate, ask questions, and interact with each other. These informal exchanges are often the most valuable part of meetings like this. Thank you very much, and I hope you enjoy the workshop.
So thank you, everyone. Our first course will be by Leticia Coniagnolo. So Leticia, go ahead.
Okay, so thank you for being here. I'm Leticia Culiandro, I'm coming from Paris. I'm Argentinian, so we can speak Spanish later on if you wish. These are my handwritten notes that were supposed to be for me, not to show them. But since there is no Blackboard, I will do it this way. I will show you my notes and I will try to expand them because sometimes they are a little bit sketchy and maybe not very well written. But anyway, this is what we're going to do today and the days after. And the content of my lectures is going to start very, very low. So I don't know exactly which is your background, but I heard that there are some students who are still in the last years of, what we would call licencia in Argentina, so the first 5 years of studies. So I guess that it's good to start from, some basics. And for those who know already, well, I'm sorry, you may be a little bit bored, but there are some comments that I will make here and there that can be useful also for people who have already seen this material in the past. So what I plan to do is you will see, start from single particle descriptions to go later in the last talk of the 3 introductory lectures to talk about many-body systems and, which are a few important features of the behavior of many-body systems in interaction, what we call macroscopic complex systems, and when they are out of equilibrium. So special features they have when they don't equilibrate with the environment or within themselves if they are isolated. So in a sense, the title of the talks is non-equilibrium macroscopic complex systems. So there are many adjectives. Non-equilibrium is because, they are not, it's not possible to describe them with the standard equilibrium measures, what you see in the standard statistical physics lectures. So we have to go beyond, and you will see why. You will see why, starting from the very simple problems of one-particle physics as already. Then I will, at a certain point, mention quantum physics, because my seminar will be about a quantum realization of active matter that we have done very recently with some colleagues. So I will mention differences between classical and quantum and similarities between classical and quantum descriptions. There are not so many differences, as you will see, but okay, some there are, and I will highlight them. The macroscopic is you have many of those single particles in interaction. We call them many body, and they're the thermodynamic limits. So the fact that you have a large number of particles allow you to use laws of large numbers and then use statistical physics, but not the standard one, because we want to be out of equilibrium. So not the one proposed by Boltzmann and you have seen in lectures normally. And complex, what do you mean by complex? We just simply mean hard, difficult to solve. And this is what makes these problems interesting, of course. So roughly the plan of the talks is, well, to start with an introduction to stochastic processes. I will start by talking about Langevin equations, because typically we will be in situations where what we're interested in is in interaction with something else, which is large, an environment, and a bath. So the simplest possible description of such a situation is the Langevin equation. So I will justify it, presenting the original Langevin's way of thinking, but also the extension that allows us to apply Langevin processes to many different cases, which go well beyond Brownian motion. So that will be mostly the first lecture. In the second lecture, I will say a little bit about Fokker-Planck description and generating functionals, and especially how these things are extended in the quantum realm, and how good descriptions they are for quantum systems, and where are the assumptions, and where are the missing points, especially in what would be the extension of Fokker-Planck out of equilibrium to the quantum problems. And then I will talk a little bit about some features of macroscopic systems out of equilibrium in the third lecture. Depending on time, I will tell you more or less. So the first thing that we have to be aware of is that we have to understand whether we want to describe a system which is closed, so isolated from the rest of the world, or whether it's open. And the description that we have to make in both cases are different. So we are going to focus on something that I'm going to always call the system. It can be a single particle, it can be many body, but it's what we are trying to describe. And this system can be, as I say, isolated from the rest of the world, or it can be in contact with the surroundings, the environment, a bath, and I will call everything else, the environment, the bath, or the surroundings in different parts of the talks. So on the first column, when the system is closed, I will use classical description. So you have that energy is constant. Okay, so from Newton's laws that if you have a Newton description of a classical mechanical problem, energy is conserved. So energy is a Hamiltonian function of positions and momenta of your particles. You can have many of them. I say it's a label that tells you which is the particle you're focusing on, and the arrows is because I'm thinking in d dimensions. So positions and momenta in d dimensions. H is a Hamiltonian function of those, and it's conserved. It's constant. It doesn't change in time. There may exist other quantities that could be also conserved depending on the problem that you have. Could be linear momentum, could be angular momentum, number of particles. So there can be other ones, but okay, the most typical and the one that I'm highlighting here is energy. Now, if your system is in contact with the environment, the energy of the system is not conserved, because there can be exchanges between the system and the rest of the world, so the energy fluctuates. And the other quantities as well, if there is the possibility of exchanging them with the rest of the world. So for example, number of particles. So if you want to do a standard equilibrium statistical physics description of these two kinds of situations, you would use microcanonical description for the left column. You would use canonical description or grand canonical description for the right column. And in all my talks here, I will be focusing on the right column. So my systems will be open. They will be in contact with some rest of the world. There are many interesting things that can be said about what happens with the dynamics of closed systems. There's a lot of activity, especially in the quantum cases, because of experiments, because of exact calculations that people can make in certain cases with certain models. But I will not talk about this But I just want to mention that, there's a lot of activity going on along these kind of problems when you look at them out of equilibrium. So we will basically focus on the right column. So if you want to describe equilibrium properties and you are in a closed situation, like in the left side of my previous slide, well, you will propose a macrocanonical distribution function for your configurations, which basically tells you that all the conserved quantities that you have are given by the initial values that you give in your dynamics. So this calligraphic I of 0, 0 is time. So those are the initial values. The thing works. Yeah. So these are the initial values. These are the functions of your phase-space variables, the positions and the momenta. So for example, this could be the total energy, the Hamiltonian. And this is the E, the value of the initial energy that you give to your system. And this is Hamiltonian. And you can have many other ones or several other ones. So this is why here I use NC, number of constants of motion. And these are the functions that are conserved by the dynamics. So this is the generalized microcanonical distribution, if you wish, where you can have several conserved quantities. Now, I told you that I will be interested in problems which are open. So I will be interested in problems which in equilibrium are described by a canonical distribution. And a canonical distribution, I remind you, the distribution function of those same configurations is given by, well, some normalization constant here, and the exponential of minus a sum over all those conserved objects when the system is closed that appear here in the exponential multiplied by some parameters. So for example, the first one could be the Hamiltonian, and the parameter that comes together with the Hamiltonian here would be the inverse temperature, 1 over kBT, T being temperature, KB Boltzmann constant. If you are in a situation in which you can exchange particles, you can also put N here, the number of particles, and gamma 2 would be the chemical potential. And if you have other ones that fluctuate because of the contact with the environment, you add them up here. And the normalization prefactor is a function of these parameters that simply tells you that if you integrate over all the possible configurations of the system, this should give you 1. So this normalization comes from the integration of this thing over here. So, but this is a standard equilibrium statistical physics that I'm just wanting to remind you the formalisms that we use to describe them, but they apply only if you can believe that your systems are in equilibrium. If they are not, you have to do something else. You have to go back to the dynamical description, the evolution in time description of your configurations, and from that evolution in time of your configurations, measure observables. Typically, when we have a many-body system, we want to measure something that concerns many particles, large portions of your system. So you define observables that depend on the positions and momenta of your particles, say, and then you measure those. And then you try to understand what's going on with the system from those measurements. So if you want to describe the evolution of closed systems, classical mechanics just tells you that you have to use Newton equations, or maybe the Hamiltonian version of classical mechanics, but just standard classical mechanics. If you want to do quantum, you have to do Heisenberg, Schrödinger descriptions of your problem. Now, if you want to consider what happens with the time evolution of an open system that is in contact with the environment, you cannot use those formalisms above just like this. You have to consider what's the effect of the environment on the evolution of the system, and you have to model that somehow. So for the problem of looking at the trajectories, looking at the time evolution of your single particles, for example, the best formalism or the best approach to do it is through the Langevin equation, and this I will introduce in a second. So it's Langevin, beginning of the 20th century, started describing the behavior of a single noisy trajectories of a particle that was doing something strange. And he was considering, how to describe the interaction of this particle, which what was surrounding it. Later on, people realized that there was also a probabilistic way of approaching this same problem that goes under the name of Fokker-Planck or master equation. I will tell you something about this tomorrow. And there are still more powerful methods which go through generating functional methods that take different names, but well, okay, this is Martin, Sigia, Rose, Jensen, the Dominicis acronym here that comes from the names of the people who worked on this in the first time, let's say. So I will tell you about Langevin today. I will tell you about Fokker-Planck and generating functional methods tomorrow. And I will also tell you tomorrow about how to make this quantum and which are the assumptions that one makes and up to where these are, believable or they're good approximations. And for that, I will tell you a little bit about Lindblad equation, which is a bit like the quantum generalization of this Fokker-Planck approach here, because I will need it for my seminar. And I will tell you a little bit about what is called Schwinger-Keldysh closed time path formalism, which is the generalization of this one. I will not use it that much, but just to let you know about this proposal, this way of calculating things, which is very powerful. It's much more powerful than this one, and it's better. It's exact in principle, while this one is much approximated. So, okay, this is more or less a little bit of a description of what I'm going to do today, what I'm going to do tomorrow, which covers this, and then I will go into the applications, say, in the last lecture, talking about many-body systems. So let me tell you about Langevin's way of introducing his equation. So at the beginning of this 20th century, there was this problem posed by Brown, who was a biologist. And what he was observing was the motion of a pollen grain immersed in water, basically in a liquid. And he was observing some just, very irregular motion of this pollen grain that it was not clear whether it was due to the fact that pollen was alive or it was dead, it was not alive, it was not an animal, say, but it was in contact with the liquid and that the liquid was making this pollen move in this very irregular fashion. Remember that at the time, beginning of the 20th century, the molecular nature of matter was not well established yet. It was not clear. I mean, people were not sure about that. So what Langevin said was, okay, he said, okay, let's imagine that this big pollen grain, because it's a big thing, is in contact with water, and that water is made by molecules, accept that they are molecules which are much smaller than the pollen grain, that they're colliding with the pollen grain and they're giving kicks to it and they're making this pollen grain move in this irregular fashion that Brown is observing. So he made a set of assumptions, very clever assumptions. I suggest you to read his paper because it's very short, very clear, very well written, very easy to read even today. Sometimes old papers are hard to read because people use different language in a sense. But this one is really written in a way that it's clear, very, very, very clear. So what he assumed was that there were many, many collisions between the water molecules and the colloid, this big sort of spherical object, which is this pollen grain. We tend to call them colloids. They're like little balls. They are little to the eye, but they are much larger than the molecules in the water. And that there are so many, many, many collisions in the unit time that you can observe. Because of course, I mean, if you go to really microscopic, if you could measure in tiny microscopic instance in time, you could maybe be able to resolve the unique single collision that the molecule was making, one molecule is making with the pollen. But of course, you cannot do that, especially at those times. So what he assumed was that, during the clock ticking that was used to measure, there were many, 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 many collisions. And that you cannot really understand, you cannot really characterize them one by one. It's impossible because you cannot access them either. So he has assumed that, and he said, okay, let's assume something about the effects of those collisions on the motion of my pollen grain. And let's assume that basically there are two effects. One's friction, something that is trying to stop the motion of that pollen grain. And another one is noise, because, okay, there was this jiggling, this, very erratic motion. So there was something that was making this pollen move in not a smooth way, in a very erratic way. So if, for example, you take one of the observations by Brown and you plot velocity as a function of time, you start always with the same velocity. And I'm not writing arrows to simplify and say that I'm measuring just in one direction. So what the assumption here is that you give an initial velocity v naught to the pollen grain at the initial time 0, which is here. And you measure, the trajectory, and you measure the instantaneous velocity. I'm not plotting position, I'm plotting velocity at different instants that you can observe with your observation way. So you would say in the first measurement, you would see something like this blue trajectory here, this blue trace of the velocity, very erratic, going up and down and so on. And then, but there is a trend here, and there is a trend that goes to eventually make this velocity fluctuate around 0. Here is 0 in this axis. So it starts with a non-zero velocity, but it goes down in some way towards fluctuating around 0. Then you initialize the experiment again. So you start from putting the same pollen grain at the same position, let's say, and giving to it the same initial velocity. And you measure, and you see a different trajectory of the velocity. Say that the orange one, something like that, it's oscillating, fluctuating, and then it goes to fluctuate around the same 0. And you repeat, and you always see something like this. Okay, so all the trajectories differ one by one if you want to look at the details. But there is a global trend here, which is that the velocity is decaying towards 0 on average. Either you do average over time or you do average over trajectories, and you always will see that those averages are decaying towards 0. And then the average will be 0, either over time or over trajectories. But the fluctuations, they remain. These fluctuations remain. So this is what I'm highlighting here with these gray vertical arrows. So the fluctuations remain around this 0 axis. And this was observed for any initial velocity that you could give in any of the directions of your system. So all trajectories are different, but they share some statistical properties, which is this decay towards 0 and these fluctuations around 0. So that Langevin said, okay, let me try to write a Newton equation, because I suppose that I can apply classical mechanics to my pollen grain. Let me write a Newton equation, force equals mass times acceleration, that will describe what I'm saying, what I'm seeing. So this is mass times acceleration, and in the right-hand side, let's write force. In d equals 1, like in my previous slide, to make things simple. But otherwise, you can put arrows. So what he said is, okay, let me separate this force from the environment in 2 pieces. One, which describes friction, the fact that those velocities were decaying towards 0. And another one that will describe the fluctuations, some random force, which I don't know the details of it, but I will characterize statistically. This was his proposal. So this first term here, basically what it will do is it will slow down the particle, kill this initial velocity. And the other one will make this thing remain fluctuating around 0, even at long times where the velocity on average has gone to 0. So the idea is that this random force, that one over there, is a function of time. At each time takes a different value, but that this value, Langevin proposes, let's pick it from a Gaussian distribution. Let's pick it from a Gaussian distribution with some average and some dispersion. And basically the only thing you need to do to characterize this stochastic process, this stochastic random force here, is to give its average over time and gives its correlations over time. So I will give you, the functional form in a second. So basically, I'm repeating what Langevin did is to say, I want something that makes the average of my velocities, and with these angular brackets here, I'm describing average. So what was this average? It could be an average over trajectories here, could also be an average over time. But let's stick to average over trajectories. So the different trajectories, according to Langevin, are generated by the different random forces psi that are acting on the pollen grain on different experiments and at different times. So on different experiments, you see at each time, different experiments feel different forces at that time. And this is why, well, basically you see different trajectories all over the place. So what Langevin said is, okay, I will have some random force that I will average over that one. And these angular brackets correspond to averages over those random forces. And I want my equation to be such that in the course of time, so with this arrow here, I'm telling you, take a long time limit, that have to make precise how long has to be this long time limit, but there will be, Langevin says, a long time limit such that this average goes to 0. And you forget in this way the initial conditions. And he asked also that the average of the square of the velocity, where you kill the sign basically, the average of the square of the velocity will not be 0. It will be something linked to what equipartition would tell you. Remember equipartition from equilibrium discussions in the statistical physics. Equipartition tells you that the expectation value of a quadratic variable, velocity in this case, or the kinetic energy, which is what I'm writing on the left-hand side here, goes to kBt of 2. I have a single variable, I'm just focusing on one direction, so this is why it's over 2 here, and kBt is temperature of the bath, so in the Brownian experiment, it's ambient temperature, kB is the Boltzmann constant. So he required that the statistical properties of this psi and the gamma, which is here, be related in some way, so as that you have both that the average of v goes to 0 and the average of v squared satisfies this relation at long times. And how long have to be those times has to be derived from the equation. So what he noticed is that if he proposed that the average over all these different realizations of the noise at a given time t is 0, and the correlations of the noise picked at different times. So I compare my noise at time t prime, at my noise at time t, and I average over different realizations of the choices of those noises. If he asked them to be proportional to gamma, the friction coefficient, kBt, temperature of the bath, and a delta function. So what this delta function tells you is that these things are correlated only if you look at them at the same time. If you look at them at different times, they are completely independent. They are not correlated. And this is representing the fact that you're measuring with a clock or with a, some measurement object that cannot measure really continuously in time. It's measuring at steps in time. And you cannot go so tiny in those tiny steps that you can really resolve single collisions. You look at a lot of collisions, and those lot of collisions add up in such a way that psi is Gaussian, law of large numbers, and they have decorrelated in different instances over which you're measuring. So with these assumptions, Gaussianity, 0 average, and these correlations only at the identical times with this prefactor here, he ensures, and you can just solve the equations, and I will do it a little bit later with a different equation, a little bit more complicated to show you how this works. So you get this 0 and this kinetic energy going to kb over t at a time scale, and I can already write it here if you wish, when times are larger than a relaxation time of the velocity, which is m over gamma, the mass of the particle over gamma, the friction coefficient. So you have a characteristic time, which is what more or less these trajectories are showing. So these would be roughly the characteristic time m over gamma when the average of the velocity went to zero and the width of those fluctuations, which is what this is measuring, goes to this kb over 2 value. Okay, so this is the content of Langevin's paper. It's just this. And what is important to know is that he made a number of assumptions here, very natural assumptions for the problem of the pollen grain, but that have to be highlighted. So basically, he assumed that there is a separation of timescales in the motion of the pollen grain and the molecules of the water. The molecules of the water are much faster, and you cannot even resolve them with your apparatus of measurement because you have all these collisions going on in a single time step of the measurement of what the pollen grain is doing. So the typical timescale for the motion of the molecules is much faster than typical timescale for the motion of the pollen grain that you can associate to this m over gamma, roughly speaking. And the other thing is that there is a separation of sizes. So the pollen grain is much bigger, and there's only one pollen grain, but it's much bigger, much heavier than the molecules in the water, that there are many more, but they are tiny. You don't even see them with your microscope, okay, at the time at least. So there is this two separation of scales in time and in sizes, which are behind his proposal for this equation. Okay, so other questions here. I'm very happy if you ask, questions, the students, basically. Well, even the professors, if they want. Questions? Yes. Yes, good, professor. Yes.
How do you find out if you have actually reached the limit in which you neglect the time scale, if you indeed have the separation of time scale?
Exactly. So I will give you one experimental realization later. So one of the applications, what the people, especially doing biology now, are doing is that they have some measurement of some tracer, they call it. So something that plays the role of this pollen grain that they put within some biological tissue or biological cell or something which is biological, and that you don't know exactly how to describe. So it's a sort of the inverse problem. What they want to understand is what are the properties of the bath. The tracer is just some colloidal particle, some little ball that they know very well. They know the size, they know the mass, they know the density, they know everything. But they don't know the environment. They don't know the medium where this object moves. And what they do is that they do just simple measurements, like, for example, they look at the traces, how the velocity of the tracer evolves in time, how the position of the tracer evolves in time. And by looking at, for example, whether really whether there is a decorrelation of the velocities, whether they go to an equilibrium situation where the average of v squared goes to equipartition or not, they conclude about the properties of the environment. And a little bit later in my notes, I have one example of those. So there are several groups which are doing that. So they're using this experiment in the opposite direction. Now that we understand that, Langevin descriptions with friction and noise are okay, they try to understand whether just this simple kind of form for the friction and the simple kind of statistical properties for the noise are good enough or not. And in many cases, they're not. So you have to generalize them. And it's also the introduction of my next part of my lectures. Okay. Questions? Yes. Other things? Okay, so as Fred and you were telling, there are many ways in which this can be generalized and made more complex and very more complicated. And actually, we use Langevin equations in very different situations, not just Brownian experiment. We use it in many different cases, and maybe you know some. We will talk about some later on. So why? Why can we always use this kind of Langevin description where you have some friction, some noise, maybe with different expressions from the ones I have just showed you? But how do we justify the use of these kind of equations more generally? So there is a way to do that, which is better in a sense, but at least more general. I don't know if it's better, but it's more general, is to model the system, but also model in more detail or in some detail, the coupling between the system and the bath, and to model the bath as well. Not just say, it's a random force and gives some friction, but just to try to make some microscopic modeling of the bath and of the coupling between the bath and the system. So in the 70s, more or less, several people in different contexts made some propositions for this, proposals for this. One was Feynman, actually, in the quantum context. There is a very nice paper by Feynman and Vernon. But there are other classical papers by Swanzig. I have the references a little bit below. And Kawasaki in Japan, who basically propose the same things, all of them, Feynman, Kawasaki, and Swanzig. And I will simplify, describe it a little bit here. So the simplest idea is to say that, imagine that you have a bath. I don't know what it is. I don't know exactly what is the origin of it. I don't know exactly its microscopic variables. But let's imagine that I can describe it with quadratic variables like harmonic oscillators. Let's imagine that, I focus on just its fluctuations, its, basic description. I do some expansion around quadratic variables, or I just propose, okay, let me say the bath, the environment, is an ensemble of NO, number of oscillators, harmonic oscillators. So these are the momenta of those oscillators. These are the masses of the oscillators. These are the positions of the oscillators. These are the frequencies and the masses of the oscillators as well. And again, I use D1 to simplify the notation. And then I will make a proposal for the interaction between my particle, the colloidal particle, let's say, the big one, and the oscillators through some coupling like this. So they're coupling constants. There's a normalization, which is handy. You will see it's useful to normalize this way here with the square root of the number of the oscillators. The positions of the oscillators, or the displacement from equilibrium of the oscillators, which would be QA equals 0, and some function of the position of my particle. It's an abstract model in a sense, but let's imagine that I can describe the coupling of my system to an environment in this way. Of course, I can make it more complicated later on, but this is the simplest one. So CA is coupling constants, oscillators, positions, and momenta, number of oscillators. And eventually, in the calculations that we will make, this number of oscillators will go to infinity. So we will take this also Langevin assumption that the environment is much larger than my particle, which is only one. And there is another term that, okay, I will discuss it a bit later, that can be added to the description. So the idea is to make a full classical mechanics description of this problem. I will have the Hamiltonian of the system, which could be just, a free particle, or could be a particle in an external potential, or could be, I don't know, some complicated particle. And this complicated particle I couple to this ensemble of oscillators in the way that is explicit up there, here. So if you write down the Newton or Hamilton equations for the dynamics of the oscillators, those equations are solvable because the oscillators are quadratic in the Hamiltonian. The equations will become linear in the oscillator positions and momenta. Okay? So they're linear equations which are forced by the coupling to x through this f of x function that is generic, which appears here. Good. So you have a classical mechanics problem where you can solve those equations for the oscillators, knowing or feeling the coupling to the particle. Now you know that to solve Newton equations, you have to give initial conditions, right? You need to give the full time dependence. This time dependence will depend on time, but it will also depend on the initial conditions. But of course, the oscillators are sort of describing all these particles in water in the Brownian problem. They're the equivalent of those. And you don't know the initial conditions of all these oscillators. So the proposal is to say that, okay, I don't know them, but I will assume that those initial positions and initial momenta of the oscillators are given by a distribution function, which is dictated by equilibrium properties. So basically, one is assuming here that the bath, the environment, is in equilibrium, is in standard Boltzmann equilibrium. So one gives a canonical distribution, e to the minus beta h, for the oscillators. Not for the particle. For the particle, you can control. So for the particle, you will give some initial position, you will give some initial momentum. But for the oscillators, you don't control them. So what you do is to say, okay, I am assuming that all my oscillators are in equilibrium at a given temperature. And here is where you introduce the parameter temperature in this description. In Langevin's description, you also did it. You did it here when you said that the correlations of the forces, the random forces, were controlled by friction coefficient, but also KBT. So you put KBT inside the game by giving these correlations for the noise. In this new approach, you are introducing KBT through this Boltzmann distribution for the momenta and positions of the oscillators. So it's an assumption. Here you're assuming that your bath is in equilibrium, and you are also assuming that the bath will be not modified by the coupling to the particle. Same thing that you did up here, because if the force was modified, the random force was modified by the pollen grain, this could not be true. I mean, it could change. Something could happen here, making this change in the course of time. But you're saying that, here, the correlations of the noise are always like this. They don't change in time. So the bath is not modified by the coupling to the particle. And it's here that you're using this separation of scales in the sense that you're using, without saying, that the bath is much larger than your system. So it's not modified by the system because the system is tiny with respect to the bath. Okay. There is a tricky issue about a counter term to be added. Okay, I will not discuss it. If you wish, you can discuss it in private because it would take time and it's a bit confusing. So let's forget about it. Now, taking the number of oscillators to infinity, the bath becomes enormous, right? Becomes huge. And you also, in a sense, using this hugeness to say that there is some law of large numbers behind that is going to make sums of objects become Gaussian variables. And these Gaussian variables appear in the distribution of the initial values of the positions and momenta of the oscillators. So the oscillators are Gaussian variables, and they are random Gaussian variables with a distribution that makes KBT and stochasticity, randomness, appear through these Gaussian variables. Okay. Now, both in the Langevin description I gave you before and in this one, the dynamics does no longer conserve energy of the system because there can be exchanges with the bath and other constant of motion of the systems if they were when it was isolated and closed. Now that it's open, it can exchange it with the bath. So it will change for the system those quantities. Now, there is a very simple calculation that once you use what I have told you about the initial conditions of the oscillators and the linear character of the equations that rule the dynamics of the oscillators, you solve them, you plug in that solution into the equation for the particle itself, the Newton equation for the particle itself, you end up with a generalized Langevin equation that looks like this. So you see, if this term was local in time, just proportional to gamma, the friction coefficient, and the delta function, you would cut this integration, and you could get here the gamma x dot that I had in my previous slides. But if you do this calculation with this oscillator description, you get a generalized friction term, which is non-local in time, and it includes memory. So you see that there is an integration over time going from the initial time to the measuring time over all times through a function gamma of time difference that I will give you the expression in a second of what it is. But it's a function of time difference. You know it. You can calculate it from the oscillator description. So this is a generalization of the friction term that appears when you do this approach with the oscillator. This F here is just some external force that you could add, like coming from some external potential. So say, for example, you can add some harmonic potential to confine the motion of the particle, or the boxes, the boundaries, the walls of the box where the pollen grain or whatever else is moving. So this is some external force. And then there is the random force here, like the Langevin one, but it takes an explicit form when you do the calculation that depends on the initial momenta of the oscillators, the initial position of the oscillators, the coupling constants between the oscillators and the system, and masses and frequencies of the oscillators. And the equation I'm writing here is actually, I should have written it, is actually one where I'm using f of x equals to x. So I'm just using a bilinear coupling between the oscillator positions and the particle position. So I have an explicit expression for the random force that depends on these initial values, which are random themselves. So here you can see where the randomicity of psi comes from the randomicity of the initial values of the oscillators. And there are time dependencies that appear here through the sines and cosines that complete the functional form of this random force. So the statistics of the initial positions of the oscillators gives you the one of the psi. And from this expression, you can compute the average value of psi at any time, and you will find that it's 0. Just if you do the explicit calculation. You can see it very easily here. If you have a Gaussian distribution for the initial momenta of your oscillators with 0 mean, okay, you will get 0 here, and you will also get 0 here, and this comes from this counted term that I'm not discussing, but we can discuss it if you are interested later on, that ensures that this is also 0. The average of this is also 0. Now, if you make the correlation between the noise at a given time t and a given time t prime, what you will find is that it's proportional to KBT, and KBT enters through, I insist, the initial distribution of the positions of the oscillators and momenta of the oscillators, times this same gamma that is here, times this same function, gamma of t, which is here, which, as I promised, it has an expression which is exact as well, and that depends on the coupling constants with the oscillators, properties of the oscillators, and some cosine function here of time difference. So you know everything. So you have built, through this modeling of coupling between particle and oscillators, a generalized Langevin equation where the friction is non-local in time any longer. The noise is correlated in a way which is no longer a delta function, but it makes the gamma appear in the same way as it appears in the friction term. So it's the same gamma. It's the same gamma over there. And the fact that it's the same gamma here and there is because you have made an equilibrium assumption for the properties of the oscillators. Had you made another assumption for the oscillators, you wouldn't get the same gamma here and there. This is very specific of assuming that your bath is in equilibrium. which is okay in many cases, like Langevin's Poland experiment or many other ones, but sometimes it's not true. Sometimes it's not true, but in those cases, you can perhaps even still use an equation of this kind with friction and noise, but friction and noise will not be related in this very simple, relatively simple way. With the same gamma here and the same gamma in the correlations of the noise, there could be something else, could be some other functional form appearing there. So this is for equilibrium baths, but you can maybe keep the same structure of the Langevin equation for out of equilibrium baths, just making this different from the statistical properties of that. And this will appear later in examples later on. So as I said, this is due to Kawasaki, Swansig in the classical literature, but Feynman and Vernon in the quantum one, same kind of approach. And what you have to do to finalize the description of the problem is to say something about how this functional form of gamma will be. I mean, what will be the temporal dependence of this gamma function here? And to do that, you have to choose properties of the oscillator. So you have to choose the coupling constants. You have to choose the I may say 1 over n here. Sorry, this is normalized in such a way that the sum goes to 1. I mean, it's order 1 when n goes to infinity. So let me correct it. Oops. So you have to say something about how this functional form looks like. I mean, what is its temporal dependence here? And that you do by normally in the literature you will see it expressed in Fourier transform way. So basically, this is the weight of the frequency omega. This expression here is the weight of frequency omega in the Fourier representation of this gamma, and normally is of omega over omega that is used in the literature. Okay, this is a typical notation or typical choice for the parametrization of this Fourier transform. And what you just can derive from here is trivial, is to see that this S of omega, which is called the spectral function, is just a sum over all these prefactors here of delta functions over the frequencies of the path. And by choosing different ensembles of oscillators, you will choose different functional forms for this spectral function, and hence different temporal forms for this friction kernel gamma. So the characteristics of the oscillators give you the characteristics of the noise correlations on the friction properties via this capital gamma. So what we have done here is we have gone from just classical mechanics. Also, Langevin did it, but he postulated the properties of the friction and the properties of the noise. Here we are deriving them with some assumptions on the bath and some assumptions on the characteristics of that bath. So we are going from classical mechanics to stochastic processes. So stochastics is in the stochastic nature of the noise. And we have also done something else, which in the context more of the quantum systems, but also in the classical, we have reduced the system. So we had a full object, which was the system, the bath, and the coupling between the two, which was closed, was not in contact with the rest of the universe. We have integrated away the bath by solving the equations on the oscillators, and we have derived an effective equation that governs the motion of the particle, which is this Langevin generalized equation that I showed you before. So we have reduced the full system from the whole to the system only, the one that you have selected, the one that you really want to understand. Okay, and by doing so, we have built a generalized equation in the general case, which is non-local in time. So it has this memory kernel here, and these non-local correlations of the noise, which are a little bit below here, which are here, so that correlate your size at different times in a non-trivial way. They're not just correlated at equal times, like in Langevin's equation for the Brownian motion, but they can be correlated at different times. And this makes the problem non-Markovian. This is another keyword that you can store in your memory, which is something that you will see in the literature, and that is typical of the motion of more complex systems. And it's typical of what happens when you do this reduction, when you make this reduction of integrating away a piece of the system that you don't really understand very well, you don't want to know all the details about, and that you characterize statistically, like I did here with initial conditions of the oscillators. I gave a distribution function for those. I give some statistical description of it, but then what remains becomes non-local in time. So remember that Newton equations are local in time, typically. I started from some local description of the whole, but then I ended up with a non-local description of a piece. So this is something that happens very often. So the Langevin case, where he assumed no correlations in time, is a particular case of this one. It can be recovered just by asking that this capital gamma be proportional to a delta function. And by choosing correctly the prefactor, then you recover the equation that I gave you at the beginning. But more generic cases can arise. So in the literature, you will see that people characterize different baths by different functional forms of this spectral function over omega that is typically chosen to be given by a power law for small values of the omega. So a growth with the power, growth of decrease, but okay, some power law characterized by an exponent here. And the literature, you will see an A-1 appear, and some cutoff function, something that makes this go down to zero. Could be an exponential decay, could be a theta function, could be something that this FC is just a cutoff that tells you that you cannot have super high frequencies in your bath. So this is a typical parameterization that you will find in the literature, but could be other ones as well, but this is just a typical case. And then you have usual cases, which is either A, this power exponent here is 1. If it's 1, you have a flat S of omega over omega, flat S of omega over omega. When you integrate the cosine, you get a delta function, and then you recover the original Langevin equation that I gave you at the beginning. Or A different from 1, and then, okay, you have these non-trivial dependencies on the frequencies that lead to different behaviors of the bath, that it will induce different behaviors of the particle itself. Okay. So different cases here, so things to tell you. So all the information about the bath is in KBT and in gamma. Now, you will see, well, just to mention that maybe you have seen Langevin equations in the past where there is no second time derivative, where there is no, where this term is not there, where you just have the friction term and you have the noise, but you don't have that one. So this usually arises when you focus on times which are longer than the characteristic time that I mentioned at the beginning for the decay of the velocity of your particle towards 0 on average, and these fluctuations towards KBT, proportional to KBT. So for times larger than gamma over m, I was calling it just gamma, so let me call it gamma. So for times which are larger than m over gamma, sorry, I'm taking it the other way. So cases when this gamma over m is very large, so that m over gamma is very small, and very quickly you reach that limit of velocities going to 0 on average, and fluctuations of velocity going to that constant proportional to KBT. So cases where you have large friction coefficient over mass, then it's licit. If you do the calculations with the acceleration, or if you do the calculations without the acceleration, just by dropping that term, you will find the same at those timescales. But if you're interested in timescales which are shorter than m over gamma, then you have to keep the acceleration. And then we'll come back to this in a second. So the cases where you drop it, it's usually called over damped. It's very damped. Friction is very large. So it's, friction is strong. It's very damped, the dynamics. And it's usually licit to use that limit in statistical physics applications, but not always. So I have to keep it in mind. So that's the cases where the momentum relaxes very, very quickly. Relaxation time is very short, and then you get this, as I said before. So you drop m x dot, and they have this separation of time scales for the system now between what happens for the velocity of your particle and what will happen for the position of the particle that will behave differently if you focus on the position of the particle. And I will show you that in a second. Now, last thing to say about these generalized Langevin equations is that if you keep the coupling between the positions of the oscillators and the position of the particle generic, so if you keep this f of x generic term like this, with the normalization, which I haven't written, so let me write it. If you do that, then you will find that this f appears here, appears there. It's actually the derivative of f that appears, and it also appears there. So what's the difference? What's the important difference about this new equation? It is that here you have that the noise multiplies a function of the position of the particle itself. So this is what is called multiplicative noise. Before, f was proportional to x, so the derivative of f with respect to x was 1. So the noise appeared alone as an additive term in your Langevin equation. And that case is called additive noise Langevin equation. Here, it's multiplying some function of x, and this makes life much more complicated. So working with equations which have multiplicative noise, it's harder in general, but sometimes it's realistic. Sometimes you have to use it. Sometimes you need to consider this kind of equations. Now, notice that the f prime that appears here is the same that appears there, and it's the same that appears over there. And this is, again, just a consequence of working with the original Newton equation, solving, introducing in the equation for the position of the particle and going ahead. So it's just a consequence of this interaction. So you cannot have something here and something else here if you start from this modeling of the coupling from the system and the bath. So this is, something that you also have to keep in mind, because if you break this balance between the f prime here, the f prime there, and the f prime there, you're working with a coupling between system and bath that breaks the assumption of equilibrium of the bath and breaks the assumption of this kind of coupling between system and bath. So you could be working with a Langevin equation which is not justified. So this is why it's important to insist and to hint, to highlight the fact that you have these same f primes here as they are there. So the countant term, I have it here. I don't want to get into those details. Actually, to really get the equations that I showed you, one extra term has to be added to the full Hamiltonian of system plus bath plus interaction. It looks like this. We can discuss it later on if you're interested. Just keep it this way and just jump over that. Now, maybe some of you have seen Langevin equations with multiplicative noise in the past, and you have seen them written in this way. So you have seen them, especially in the mathematics literature. You can see people working on statistical processes with Langevin equations written this way, and in finance, in all sorts of different applications. So first thing to notice is that there is no inertial term, so there is no acceleration. So the overdamped limit has been taken already. So the acceleration term in the Newton equation has been dropped. So this equation, if you want to describe a physical problem, concerns only times which are longer than this inertial time m over gamma that I told you about at the beginning. The other thing is that you see that the friction is local in time. It's not, it doesn't have this memory here. Okay, so in this equation, the capital gamma has been taken to be proportional to the delta function in a way which is twice this gamma prefactor, this gamma friction coefficient. So this has been also done as an assumption, applied as an assumption to this equation here. So the integral has been cut, and this has been made local in time. But of course, in this equation, you still have the f prime squared here, and you have the f prime there. But then you divide by f prime on one side and on the other. So you divide by this here and there. This divided by f prime square will be another form of force. So it could be this f bar that appears here. And the G will be the little f prime, well, 1 over little f prime, no? Because if I divide here and there, I get a 1 over f prime, and this will become the G. So this equation that appears typically in mathematical literature in different kinds, and also in the physical in some cases, has made already this set of approximations on the most general one that I wrote before. Has made the overdamp limit, dropping this one. It has made the no memory limit, making this be proportional to the delta function. And it has set gamma to 1 just by a redefinition of time. This you can make with just renaming time and eating up gamma in time so that the gamma doesn't appear there and doesn't appear in the correlation of the psi either. So just to tell you that, if you have seen this multiplicative noise equation in the past, is compatible with what I wrote you before, and it only appears on after a number of approximations have been made. I have written the force here, the external one, as being a function of the position of the particle and maybe some external parameters, lambda. This could be some parameters that can be tuned by the experimentalists. I will give you some examples in a second of these. This is why these lambda appear. You could have found them a little bit mysterious, but this is why they appear there. Okay, you can generalize these to multivariable cases, make it, live in higher dimensions. You can make a lot of other generalizations. What is interesting to see here is that although this equation is non-Markovian because it has this integration over time, the integration over time goes up to the measuring time t, doesn't go beyond it. So the equation is causal. What happens at time t depends only on what happened before that time t. It doesn't depend on what will happen later on. So it doesn't break causality. You don't want to break causality usually. So this is a property that I have to stress here. So this is due to causality, and that is nice. And okay, this is lambda t, as I said already, is a possible time-dependent parameter that you could make appear in your external force. So for example, if you have a harmonic potential in which your particle is moving, you can move it. You can change the width of that harmonic potential in time with some procedure, and this could be interesting. And these kind of things have been done experimentally. I will tell you in which context. Okay, here I have some references. So I have actually a review article, which basically the set of lecture notes on these that appeared in Advances in Physics recently, where all the calculations are there. If you want to have a look at the calculations, it's quite detailed. Yeah, they're also available in my homepage here through this link. And it's also the same is in Advances in Physics. And there are some sketchy slides in this place for some conference that I gave, some seminar I gave some time ago. And the stress was there on the no Markovianity. So this is why they're called this way. Okay, I'm doing that bad in time. So this is my prediction, and more or less okay. Okay, so now let me tell you about some applications, because this was sort of formalism. Let's talk about some applications of these. Other questions? No questions here. Okay, so let me tell you about some modern applications of Langevin equations. The first one I had in the list is this inverse problem I already mentioned following Fred's question, which is that you observe the motion of a tracer, like in Brownian motion. So you use a ball like a tracer and you immerse it in some medium that you don't understand very well. And you want to conclude about the properties of the bath from the motion of the colloid. So in a sense, Langevin did it this way because he observed the motion of the colloid and he inferred which were the forces that were leading to this motion, forces coming from the bath. So this is what he did. Now people are doing this in more complicated situations. And there are loads of experiments, especially in cellular environment and biological situations. For example, Pierre Ronceray, who's working in Marseille, is one of the ones who are trying to understand from the motion of the tracer, which are the properties of the bath. And it looks like a very simple problem, but actually it's not. Why? And some of the reasons why it is not is that because you cannot measure over very long periods of time. So of course, the time spans that you can measure experimentally are limited. So you don't have infinite time trajectories. You have, finite time trajectories. There is also this clock, that is ticking with some periodicity over which you measure. So my continuous lines that I plotted in the sketch at the beginning, of course, they are not continuous. You only have discrete points, and you don't know what happens in between. So you have the discreteness of the measuring procedure, you have the finite length of your measuring procedure, and you also have the finite number of trajectories that you can measure, right? So you are limited statistically by those numbers that you can try to improve, but of course you will always be limited. So you need to make very, advanced, you have to use very advanced methods of statistics to do this inference evaluation. And this is difficult. And so there are many people who are doing that. Pierre is one of the ones who's doing it in France, but there are groups at MIT and many, many others. And it's an interesting problem. So linked to what Fred was asking, for example, these people in MIT, what they were doing was they were measuring the correlations of the positions of the tracers at different times. So they get data points that they fit with some functional form. Okay, this is very complicated functional form. This is the one that gives the best possible description of their data. And it turns out that this complicated functional form, which even has a name, is something that decays, of course, in some way. But it's the thing that you can get if you use a Langevin equation with a gamma kernel that has some time dependence in it. So by measuring this, you infer about the gamma, capital gamma of the bath. And this is what these people have done, in a series of experiments in the past, like 20 years ago. Of course, there are better measurements now, but just to give you an idea that this inverse problem is interesting. There are other people who are doing a little bit like what you were asking. So imagine that you have a system which is coupled to two baths. Maybe the pollen is on the interface between, water and oil, and what the pollen will feel from the bottom because of the oil is going to be different from what it feels from the up part of it because of the water. So there will be two baths, different baths, maybe both of them in equilibrium or not, but certainly different, coupled to your system. So this is the system, and then you have the two baths. So maybe you can describe this problem by using a combined description of your bath. So you have gamma 1 for one bath, gamma 2 for the other bath. They can have different functional forms. Then you have the noise-noise correlation. So you have the noise from one bath, the noise from the other bath. They can have different gammas, but maybe also different temperatures. Perhaps, perhaps you are heating the oil and you're cooling the water, and then the temperatures of the two are different. And maybe the two are in equilibrium at their temperatures, but they're different temperatures. So then there will be heat, going from one part of the system to the other, some transfer of energy going on. So then the particle will feel a bath which is not in equilibrium because it's a combined bath of two pieces which are perhaps both of them in equilibrium, but the two of them are not in equilibrium between themselves. So for these systems, there will be transfers of maybe matter, maybe energy, maybe, I don't know, something else. So there are typical problems which are studied in the context of transfers of things, transfers of quantities. And this is typical a situation which is explicitly out of equilibrium. The coupling to the bath is taking your system completely out of equilibrium, and it's inducing currents. So, okay, this is another possibility. Problems can be forced externally. This is the external force that can depend on the position of the particle, but then you can do, this external forcing, like, for example, changing the confining potential or doing different kind of things to it through a time variating parameter, lambda of t. And this is the setting which is used in the studies of fluctuation theorems that maybe you have heard of. Problems which are also keywords that appear are entropy production, stochastic thermodynamics, these kind of fields that have been very, very, very active in research in the last 20 years or so, where people have, considered the effect of changing externally some properties of the external forces. There are problems which appear also in cosmology, if you want to know, because there's also, external potential that is tuned in problems of inflation and so on. So people doing cosmology are also doing stochastic processes, and they're also doing problems where this forcing is externally changed by God or by somebody. Okay, and then another kind of application of these Langevin equations that certainly Fred will talk about, and I will also talk about a little bit later, concerns active matter. So active matter is the global name that is given to biological systems such that their entities, their constituents, get energy from the environment, and they use it to move. So it's like, eating. An animal is eating from the environment and it uses it to move from one place to another. Or a bacteria is eating from the fluid in which it's living, and it's using it also to move and to do some collective motion. We will talk about collective motion later on. Move in some strange way and do things together. So there are different ways of modeling active matter. There are different microscopic models for the motion of each individual in the global system of many of these, the collective ensemble, but we have to start from the beginning. So we have to start from the single particle description. And for the single particle description, one of the classical, say, active models for active particles is called active Ornstein-Uhlenbeck particles. And what these models are very similar to what I told you before. So imagine that you have a particle in the overdamped limit, so no acceleration. There is a friction coefficient here, no memory for the friction. So this is just the velocity, friction coefficient, some external force, and some noise. But the noise is chosen not to be directly related to the friction that appears in this Langevin equation. It's chosen to follow a different evolution equation, which is here. So this is the velocity of this noise that follows a Langevin equation itself with a term here, which is a force. It derives from a harmonic potential. It's the force that you will get from deriving an eta squared with respect to eta. So this is why you have this linear term here with some characteristic spring constant, which I'm calling 1 over tau, because this tau is going to be a time, plus another noise. And this other noise has zero average and correlations as in the original Langevin equation, so a delta correlated times temperature. So this is the model. So you propose this, and this model, you see, already looking at this first line here, you notice that this friction and this noise do not come from an equilibrium bath. Because if they were to come from an equilibrium bath, the friction here should be the one given by, so the structure of the friction term should be the same as the structure of the noise correlations. But if you calculate the correlations of this eta noise, and let me see if I have time to do it carefully. Yeah, I can. So I will do this in a second, but if you look at the correlations of this eta noise, you will find that they go like an exponential function of the time difference over this tau, the same tau that is over there. So it's not the delta function, the correlations of the eta. It's this exponential decay. So this line here is not of the form that I gave you before for the generalized Langevin equations, where the local in time friction here should be also linked to a local correlations of the noise which appear here. This is broken. The correlations of the noise are non-trivial while the friction is local. So this is telling you that the bath with which this particle is in contact is out of equilibrium. And this is mimicking this issue of eating energy from the bath and making this particle behave in a special way that I will show you a little bit later, maybe today or tomorrow. So how do I know that eta is correlated in this way? Well, what you have to do is you have to solve this equation, but this is a linear equation, the linear differential, first order linear differential equation for eta. So you can just simply integrate it. You integrate it like this. This is the exact solution to this equation. You can just verify it yourselves. This is the initial value of the eta that you assume, okay, it's 0. Let's say it's 0. There is this exponential decay, but okay, I set it to 0, so this term disappears. Here you have this other noise psi that appears. So if I calculate the average of eta, this term is 0. This term is 0 because the average of psi is 0. So eta has 0 average. But if I compute the correlation of the psi with itself at a different time, there will be a term coming from here that correlates the psi at different times. But there will be two integrals, you see, one up to time t, another one up to time t prime. And this delta will cut one of the integrals, the other one will remain. You calculate the integral and you get here. So the etas are correlated non-trivially, and this is just a trivial consequence of this equation. But you started from this equation where the friction was local. So this is why these equations are describing an out of equilibrium bath influencing the motion of my particle. So, okay, the details of the correlation of the noise are here. You can do it yourselves. This was just for me to check that I was not missing constants. Okay, I can check that. So, okay, I'm exactly on time. So I will finish here. I can also measure that there are other applications of Langevin equations, which are very fashionable nowadays, which are linked to the behavior of generating, AI models. Those models where you generate figures from or images or photographs from other photographs that you feed to the equations. Those are modeled by Langevin equations that go back and forth. If you want to know more about that, we can discuss it in private. But okay, just to say that the field is or the approach, let's say, the formalism is very useful. So it's something that you have to know if you don't know it yet. Thank you.
Thank you very much for the class. I do have a little question, Sam. It has to do with the normalization term that you have for the Hamilton.
The constant, yeah.
Maybe you can comment on it.
Yes. So if I don't put it, which is I didn't explain, the exact calculations, but if I don't add it to the, let me go back. Where is it? Here it is. So if I don't add this counter term is called to my full Hamiltonian, what I will get is I will get my I will get a force on my particle that is like a harmonic coming from a harmonic potential because of the coupling to that I use, which is in this case linear in X, because between the oscillators and the particles. So I will get a force in my Langevin equation that is coming from a harmonic potential with negative curvature. And this can make the dynamics of your particle unstable because you can take it to minus infinity, or it changes the behavior that you want to describe for the motion of your particle in the potential that you want to consider, in the actual external potential that you have. So through the coupling to the environment, you also induce a force which is not external, which is due to the bath. So then it's sort of a philosophical question whether you want to keep this force or you want to kill this force. And depends on the context whether you do it or not. So typically in classical applications, you say, I don't want that effect from the bath on my particle. So I add this counter term and I just remove it this way. But in other situations, you cannot do it. You cannot argue that. You really, the bath is doing, it's also changing a force. It's also inducing a force on your particle that you have to keep. It depends on the context. So to get this equation here, I have to add the counter term. If I don't add that counter term, I would basically get a term here with a plus on the right-hand side with some prefactor, let's call it k, times an x. And if I have, f of x, then I will have here something that comes from the f of x, some force that is not necessarily linear. So it's a bit of it depends on the context. So you can, in the quantum cases, you can certainly not drop these terms. Exactly. So in the quantum case, the effect of the bath on your selected part that you want to describe is very strong, and in these terms will be non-local. Sorry, they will appear like non-local contributions to your description in time that you cannot just say I drop it. In the classical case, it's more justified. So yeah.
Okay, another question.
Is a question over there?
Thank you for the class. I have a question about if you put an external condition on the temperature of the bath, at example in the Brownian movement until, I don't know, freezing down the water, how does this thermal condition changes the equation, like in the noise and in the friction?
Exactly. So the simplest thing that people do is just to say, for example, let me say, where am I? So that just to say, for example, here you see they have KBT. So maybe one of the possibilities is to just to say that if you change the temperature of the bath, you put a temperature that depends on time over there. This is one of the simplest approaches, let's say, or theoretical descriptions that you can make. This has been done, is done in certain cases. So you can say that you anneal, for example, your problem. Annealing means that you slowly change the temperature of the, you cool down your system by changing slowly the temperature of the bath. And then what you simply do is to say, okay, I can put a T of T here, and I choose the way in which this T of T changes in time. And that's the simplest one. But of course, I mean, in some cases can be a bit of a simplification, oversimplification.
Can I comment on that?
Sure.
So there is a 1990 paper by Javier Rey and I think Casado, in which they do exactly this. And they start from exactly your description, and they assume the bath is in local thermal equilibrium at varying temperature. And then they find out that there is an extra term in the Langevin equation that is just a linear term.
Yeah.
That involves the speed of relaxation of the temperature. So if the relaxation of the temperature is fast with respect to whatever is happening in the interesting system, but they also comment, and this is something that I always wanted to investigate, that this is now the extra term that they get is very bath modeling dependent. Whereas your stuff here, you use harmonic oscillators, but we know it's true somehow generally.
Yeah.
But for the non-equilibrium situation, we have no clue, I think, what's happening.
No, I fully agree. This is why I said that it could be an oversimplification, but we do it quite often. I mean, when we try to do dependencies on cooling rates, it was very fashionable in some years ago to do these Kibble-Zurek measurements. I don't know if you heard about that, but it also came from cosmology, people cooling down the universe, but then, you cool down materials, and you cool them down with some procedure across a phase transition, for example. So typically linearly in time, you change temperature across a phase transition. And to simulate analytically this kind of process, the simplest thing to do is to say, okay, I change this temperature linearly in time. But it could be an oversimplification in some cases, yes.
Okay, we have time for one more question.
Hi, thank you for the class. I was going to ask you about the Ornstein-Uhlenbeck model. Just why would it be convenient to use this different eta that is exponentially correlated in time for describing these biological systems?
Yes, okay. We'll certainly talk a lot more about that. Maybe Fred, for sure, I will do it in my seminar in the last lecture. And the reason is that many of these biological particles, they don't do a Brownian motion like the one I showed you before. What they typically do is that they move in sort of straight lines for a period of time, and then they change direction, and then they change. Of course, there's fluctuations around the straight line, but grosso modo, it's a straight line, then they change direction. And this persistent time is called, this time over which they do these linear displacements along a direction, is controlled by this tau. So with these equations, you can mimic, you can describe this kind of persistent Brownian motion. So this is why the correlations in time that you have here in the eta are the ones that are telling you that basically the noise is more or less the same that you feel over this period. So then you just do ballistic motion along these lines, but then it changes because, okay, there is a relaxation time there, which is stop. And then is when the direction changes and this reproduces itself. So these equations, this model is able to describe that observed behavior. And this is why it's preferred to describe these persistent Brownian motions than the usual Langevin standard one.
Okay, thank you, Leticia, for
Thank
this first session of the tutorial courses.
Thank you.
Now we have a coffee break, and we return to another session at 11 a.m. Thank you.
Thank you. Je le connais pas celui-là.
Sí.
Hola, hola
Hola,
Jorge, ¿qué tal?
¿qué tal? ¿Me
Buenos
escuchás?
días.
Sí,
Mm,
¿escuchás bien?
Escucho. A
Bueno,
ver, espérame, estamos viendo si te podemos escuchar. ¿Tú me escuchas?
sí, yo sí.
Es mi marido.
Ah, sí.
¿Qué va
A
a
ver,
hacer?
vamos. Ujú.
Es el volumen de...
Hola Jorge, ¿me escuchas?
Sí, ¿vos?
A ver.
Eh, yo sí,
Ahí intentemos. ¿Me escuchas, Jorge?
sí.
Listo, hola. ¿Qué tal?
Hola, hola. ¿Vos me escuchás?
Sí, sí, te escucho. Ya te escuchamos aquí en el auditorio. En este
Ok.
momento estamos en coffee break,
Sí.
pero a las 11 ya empezamos tu conferencia.
Y
Eh,
share tengo que hacer yo, ¿no?
sí, puedes compartir tu pantalla. Yo voy a dejar de compartir y ya.
Y
Entonces,
la comparto después, ¿no? O cómo, o sí.
si quieres, puedes compartirla ya mismo y dejarla ahí como la
Bueno,
primera.
hagamos así.
Luego yo
Eh,
te parece. Empezamos.
espérate un
Empezamos.
segundito. Ok.
Y vemos ya tu pantalla en el auditorio.
Eh, bien. Ahora tengo que, supongo, hacerla que ocupe todo. Mm,
no está ocurriendo. Espera un segundo. Oh, lo hago en sistema primitivo.
Listo.
¿Y está bien ahí o
Ahí
se
ya
ve
vemos tu presentación.
se ve la
Puedes
cosa
poner-
de abajo, ¿no? No. Mm. ¿No hay una manera de que haga full screen?
Sí, en la curva debe haber una
Ah, en
opción.
view, por ahí.
Ujú.
Ahí me gusta más.
Está perfecto. ¿Listo?
Listo.
Entonces, dentro de 10 minutos empezamos. Por aquí ya en el
Dale,
auditorio.
dale. Ah, ¿en qué idioma?
Hola.
Hola,
Hola.
hola, hola.
Ya. Eh, pues mira, hay algunas personas que están en inglés. Si prefieres en inglés, sí,
Me da exactamente lo mismo. Exactamente lo mismo.
por en inglés.
Ok.
Gracias, Jorge. Hola Jorge, ya vamos a
Hola.
empezar, entonces en un par de minutos empezamos.
Dale.
Tu nous entends?
Oui.
Bonjour, Jorge.
Salut, ça va?
Super. Ne dis rien, ça, tout est diffusé dans l'amphi.
Ah, ok, ok. Je te demande pas sur les empanadas, alors.
Bon, allez, à plus. Bon talk.
Ok. Non, toi, bon talk. À toi.
Hola Jorge, mira. Hola.
Hi, Jaron. How are you?
Oh, good. How are you?
Fine. Hmm?
Sad that you're not here.
Yeah. For your first time in Bogota?
Yes, indeed. First time in Colombia.
I had never been there. I mean, only virtually now.
Ok, chao.
Fred? Fred?
Ouais, je t'entends.
Est-ce que tu peux retourner la caméra, comme ça je vois les gens ou non?
Ah, es que ¿quieres que la cámara tome el teatro si se puede? Ouais, attends, il s'en occupe.
Non, oui, si c'est pas trop compliqué.
Okay, now we continue with a session with 3 talks. Our first speaker is Professor Jorge Kurchan. He is going to present the talk to the abnormal response measure chaos. Jorge, thank you very much for your participation in this workshop. You can continue.
Shall I start?
Yeah, thank you.
Okay. Tell me when to start.
Jorge, you can start.
¿Empiezo?
Sí, por favor.
No escucho.
Hola, Jorge. Puedes comenzar. Hola, Jorge. Puedes comenzar.
Ok, ok. Bueno, I'm going to speak in English, but es un placer estar, aunque sea virtualmente, en Bogotá. Espero en alguna otra ocasión estar en carne y hueso. So, I will talk to you about this work we were doing years ago with Kandang, Nguyen, Toulam, and Tomer Goldfriend. So, when you ask a question like, how chaotic is the solar system? How do you measure chaos? So the traditional way to measure chaos is the Lyapunov exponent. What you do is you consider two nearby trajectories and then let them evolve and then see how their neutral distance grows. And Mr. Lyapunov decided or showed or guessed that it grows exponentially, this distance with time, in a system that is chaotic, or perhaps it doesn't grow at all. When it grows exponentially with this exponent here, then we say usually that the system is chaotic. Lambda is called the Lyapunov exponent. So there are systems, and you are familiar with the harmonic oscillator or the Kepler problem, that are integrable, meaning that the motion is very particular. It is kind of in phase space laminar. It's very organized. And this happens when there are many constants of motion. These are what we call, in general, integrable systems. And if we look at it in the space, or in phase space, what we see is that the motion takes place in a torus. The torus is precisely given by the constants of motion. So what you learn when you study mechanics is, how do I measure it? How do I describe it this way? Well, you have the equations in the action angle variables. The angles are the angles that circle around the ears of a torus. And the constants of motion, I, they are constant. And so this means that the Hamiltonian is an exclusive function of the constants of motion. This would be a typical integrable system. Now, what happens when you have a system like the solar system, which is almost integrable? Each planet is a Kepler problem, and we know that the Kepler problem is integrable. So there is no chaos, so everything is okay. But, however, the different planets perturb one another. That's where the word perturbation comes from. The planets are bothering one another. And this breaks integrability. And the question has been, since the old days, how much? And so what happens when you perturb an integrable model? An integrable model has these very smooth orbits. Once you perturb it, there are regions that become chaotic. You can see here in the middle, there are regions that immediately the motion is no longer smooth and laminar. So, okay, Kolmogorov, Arnold, and Moser showed a theorem that said that when you perturb a little bit a system, at the beginning, with small perturbation, there are regions that are okay. They don't feel the perturbation. However, there are other regions that do. But the important point of this theorem is that it shows that you can be lucky and, in spite of having a perturbation, still behave as if you were regular. In particular, if you started in these lucky places, your Lyapunov exponent is going to be 0. And you will feel just as in a normal system. I think, I'm not sure, that there were days when people thought that this meant that perhaps the solar system was living in one of these tori. Perhaps the solar system was not chaotic. And this thanks to the KAM theorem. But nobody believes that anymore. And by now we realize that it wasn't reasonable to believe it was going to be that way. So we have the solar system with a number of planets, and thanks to computers and to better methods, people have calculated the Lyapunov exponent. So we are sure now that we are not in a smooth region of motion, and the Lyapunov exponent turns out to be enormous. The typical time, so it's the inverse of the Lyapunov, is 5 million years. So you realize it's very, very short time. 5 million years ago, our ancestors, more or less ancestors, were around. It's not even a geological time. It's really a short time. This was done by Laskar and Sussman Wisdom, who with better computers and sharper methods managed to measure this quite okay. So we have a bit of a mystery, because when you look at the stability of the simulated solar system, you find that nothing happens for almost 5 billion years, 5,000 million years, which is the age of the solar system also. And by that time, probably Mercury will be kicked out and maybe knock Venus on the way, and all hell will break loose. But in a much, much longer time, in a time that is in the future as big as the age as we are now from the beginning. And even if you didn't have Mercury around, there is this difference. So we have this enormous difference between the time estimated from the Lyapunov exponent and the time, the really interesting time, which is the time at which the solar system will simply fly away. Now, so one idea one can have to understand this a bit more simply, more like a statistical mechanics people and less like a traditional mechanics person, is to imagine that you have one of the planets, for example, Neptune or Mercury, and consider it doing its Kepler thing, but treat the influence of all other planets as if it was only a noise acting. So instead of solving the equation for the rest, I treat the rest as a given noise. And a noise is a time-dependent force. And what would that do? So what we are led to studying is the equations of motion of the planet, Hamilton, Newton if you want, under the influence of a noise. And this we can do even for a system of 1 degree of freedom, which is what we're going to do now. So we perturb a dynamics with white noise, and we just see what happens. So we now go to the action angle variables, as I promised, and this term would be 0 if there were no noise, and this is, just saying that the constant of motion is constant. And this one is 0, which is just saying that around the ears of the torus, you're just turning constantly. Okay, you solve this. I don't have I cannot give many details, but it's not particularly difficult. We are now in 1 + 1 variable, 1 moment and 1 coordinate. Here we use, and it connects with a lot of lovely stuff done years ago by Bert Halperin, Elizabeth Garner, Bernard Derrida, Kiron Malik, Philippe Marc, a lot of people, and it connects with a lot of nice work on localization, etc., etc. If you ever want to read it, it's worthwhile, it's a nice read. But okay, you use what you have to use, and you conclude that you get a Lyapunov exponent that depends on the amplitude of the noise as a power 1/3. And this is very surprising because, by the way, let's be clear, the two trajectories that produce the Lyapunov exponent have the same noise. Otherwise, they would separate just by diffusion. They have the same noise, but they start in slightly different places, and we get a Lyapunov exponent. What happened with the KAM theorem I mean, we were supposed to say that when you perturb a system a little bit, some of the integrability doesn't break. But here we find it breaks immediately. Just with any non-zero amplitude, you get a Lyapunov, that is the noise to the 1/3. Well, you can sort of reconcile, of course, the Camp theorem wasn't made for this, and by saying that white noise contains all frequencies, so it destroys everything, it resonates with everything. Okay, so when you solve it concretely, you discover that if you had no noise, the two trajectories would be moving on the torus. But what happens when you add the noise is that they begin to separate in a kind of Lyapunov manner, but they separate along the surface of the torus. And only once in a while, this distance between the two trajectories flips and they exchange places and they continue. So two trajectories with the same noise diverge exponentially, but in a very bizarre way, and this the solution tells you. They diverge exponentially, but at the beginning without moving out of the torus. Okay, so I'm going to be fast. So you can solve everything. And you conclude that indeed, when you look at the separation between trajectories, it grows exponentially. And these blips you see are the moments where the slip happens, when they turn, as I mentioned before. This all comes from the solution. And now you look at the true simulation of Pluto and Saturn. Pluto used to be a planet until a few years ago, but it lives and it's bothered mainly by Jupiter and Saturn and Neptune. And you see that when this is the separation of trajectories, and you see that the behavior is identical. And this one is Saturn. So you see this thing that is simply a system, in fact, a quartic oscillator under the influence of random noise, and the true Pluto and the true Saturn behave very much in the same way. And you have these slips where the distance flips, exactly following, or more or less following, the law that you get with the calculation. Okay, I'm not going to continue, I don't have time, but you can play the same game with more complicated problem. This is an integrable chain, the Fermi pasta, it's a chain, the Fermi pasta Ulam Tsingu chain, which is also, you can think of it as an integrable plus a little perturbation. And I'm going to make this very short. You have the same dichotomy between a very quick, very short Lyapunov time and a very long thermalization time. So what do we conclude from this? That Lyapunov exponents for these kind of problems, which are almost integrable, paradoxically have the perturbation has a very big effect, but it gives you a very big Lyapunov exponent, an incredibly big Lyapunov exponent, but it's not telling you that the system is moving in any direction. Most of it is separation of orbits within the torus. In other words, without changing the constants of motion very much, only changing the angles. So it's not really useful chaos in the sense of destroying the solar system. The solar system has a Lyapunov exponent of a Lyapunov time of 5 million years, but you can be reassured the lifetime of the solar system is probably going to be much longer than 5 million years. And why? Because almost all the chaos that is happening is keeping the constants of motion constant on the torus. So I think my time has run out. Thank you very much.
Thank you, Jorge, for your talk. Now we have a couple of questions. Do you have one question?
Hi, Jorge, it's Jaren. So if the Lyapunov is not very useful for understanding something like the lifetime of a complex system, do you have any idea of an alternative calculation that would give, say, how long the solar system should last?
No, what people do is for a weakly perturbed integrable system is they study how do you diffuse away from the torus. And this is an easy calculation. It's just kind of noise makes you move out. Perturbation is like noise and it makes you move out. So if the Lyapunov goes like epsilon to the 1/3, the diffusion goes like epsilon squared. So it's much slower, but this one is much more realistic. It much more useful. Tells you how a torus moves into another torus. And then eventually all hell breaks loose, no? For example, when Mercury hits against Venus, for example. But that is a better measure, for sure. And this is what in quantum mechanics they call Fermi golden rule calculation, which always is the same idea. You diffuse rather than make a Lyapunov instability.
All right, thanks.
Other question?
Professor Kurshan, thank you very much for the presentation. So as far as I understood, these flippings among different states maintain the, let's say, the stability of the system despite the fact that the Lyapunov exponents are positive. Is that
Yes. The flippings are also not happening in reality. They are the flippings between the distance between two trajectories that you're using in your computer. But when you are observing a system, you don't see any flipping. You see just the motion. In any case, these flippings bring you from the torus, make you turn around very quickly, but you go back to the torus. So all trajectories at the beginning move just within the torus.
Okay, so the flippings bring the system back to stability.
Yeah, yeah. The time for diffusing away from the torus exists, but it's much, much, much longer. So one would be the 5 million years, and the other one would be the 5,000 million years.
Okay, thank you very much.
Another question? No more questions. Thank you, Jorge, for your talk.
Bye-bye.
Okay, now we continue with the talk of Jaron Ken Dobias. Talk is titled Very Persistent Random Walker Reveal Transitions in Landscape Topology.
All right, thank you for the introduction. I'm going to be talking today about some work that's motivated by optimization in random landscapes. So you might think of a random landscape as being sort of like this, a very disordered structure, and optimization would be something like trying to find the maxima of this structure. Now, as physicists, we never find maxima, we always find minima. So I'm going to flip it upside down so that we're looking for the minima of this now. And a classic way to do this with optimization is to start an algorithm like gradient descent by picking a random configuration in the landscape and then following the slope downhill till we reach a minimum. And this gives us an optimum. Maybe not the best, but one optimum. If you repeat this procedure starting from different points, we find different optima. And sometimes these can look qualitatively different from each other. Like for instance, this one is very flat. Now, in the physical systems we usually study, which are very large, and therefore have very many dimensions effectively, the outcomes of optimization like this approach a deterministic outcome in that large size limit. And we can make statements about how optimization performs that with high probability will be true. Like for instance, we know that in very high dimensional landscapes, it's much more likely to end up in a flat region like those highlighted here than near the peaks, for instance. Now, one thing that's been very long known about optimization of random landscapes is it can be impeded by the presence of many metastable states or minima. But this isn't a very precise heuristic. You know, in this cartoon I've drawn here, there are many different proliferations of minima at different levels in the landscape. And it's, you know, they qualitatively look kind of different from each other. And it's clear that maybe some of them won't impede optimization, but others will stop you from optimizing further. Now, there's been a lot of recent work improving the precision of understanding at what point optimization gets stuck in the landscape, using, rather than the statistics of minima, the properties of the level sets of the energy. So there's long, deep mathematical connections between these two things. From Morse theory, we know that the level sets, which are the slices of the energy at a certain constant level, they change when you pass saddle points in minima in the landscape. This is an old result of Morse theory. So there's a deep connection between level sets and minima. And you can see here as well in my cartoon, as I move down in the landscape, passing through different minima and saddles in the landscape cause the level set to be split into different pieces in qualitatively different ways. So the kind of key result that was recently shown in this vein was something called the overlap gap property, which can be shown to bound from below the performance of a wide variety of algorithms in polynomial time. And this overlap gap property is related to the presence or absence of a large system spanning component of the energy level set. So that's one example of progress in this field. So to be more concrete, I'm going to talk about a specific model. The models I'll be talking about today are the spherical spin glasses, which are mean field spin glass models that consist of random polynomials on the surface of a high dimensional sphere. There are two basic types of these models for the purposes today. Pure models are homogeneous polynomials on the sphere, and mixed models are inhomogeneous polynomials. That's what we have to know. So these models have been, oops, did I lose I might have pressed some button. I pressed the bottom button. Can you put this again? If I ever press the bottom button, it stops working. There we go. All right, so if you, the properties of the stationary points, the minima and saddle points of these pure spherical models have been studied extensively for several decades, and they have a very peculiar structure. So in the pure models, at every energy density in the landscape, you find only one kind of stationary point, either saddles of a certain index or minima of a certain stiffness. And this means this sharp division between saddle points and minima can be expressed by a certain energy density, the so-called threshold energy density, which divides above all saddle points from below all minima. Now, this structure has implications for the topology of the energy level sets. In particular, it means that as a function of energy density, with very high probability, you will always find a single connected component above the threshold and many small disconnected components below the threshold. And this means that the algorithmic limit implied by the overlap gap property coincides with the threshold, as does in fact the outcome of basically any optimization you like to do, gradient descent, annealing, or a very fancy algorithm like approximate message passing. All of these methods will end at the same energy density in these models because of this structure. Mixed models, however, have a very different structure. In mixed models, at each energy density, you find a mixture of different kinds of stationary points. It's more generic in a sense. And you can still define a threshold energy as the energy density which divides most of the saddle points in the landscape from most of the minima, but it's no longer a sharp transition. There are many minima above and there are many saddles below. This also has implications for the energy topology of the level sets. No longer is there a sharp transition from connected to disconnected. Instead, the level set breaks up into small pieces over a range of energies, and you find a large connected component even below the threshold potentially. Now, this means that the algorithmic limit set by the overlap gap property is below the threshold. So very clever algorithms can go below the threshold. And a natural question is, okay, we know from actually other work that different algorithms in these models reach different endpoints, which maybe is natural. So the question that's going to motivate the rest of my talk is, how can we talk about which energy density should attract the most simple kind of dynamics, gradient descent, kind of the stupidest optimization algorithm you can make? Now, gradient descent being a pretty simple algorithm, I'm going to make a kind of heuristic argument about where it should go, and then we're going to talk about how to compute this property. Gradient descent, one imagines, because it's so simple, it only just follows the downhill direction. it is likely at all times to always belong to a typical piece of the level set. So it's unlikely that it ends up in a rare part of the landscape. Now, we also know that the moment a descending algorithm enters an isolated part of the level set, it'll be stuck at about that energy density. So it goes to figure that gradient descent will become stuck at the first energy density at which typical configurations no longer belong to a big spanning component, right? So the overlap gap property talked about when such a component existed, but we want to ask, when is a large spanning component typical or atypical? Now, it's one thing to state this as a guess for how gradient descent should go, but it's another thing to actually compute in a mean field model, for instance, what is this energy density? And the way that I'm going to talk about doing it is with random walks. Basically, the idea is simple. You start a random walk somewhere random in the landscape, and you let it evolve. And if the random walk's correlation function decays to 0, then you know that you started the random walk on a piece of the level set, which was a large spanning component. As a quick aside, you make the random walk stay at constant energy the entire time. So it's kind of a micro-canonical Langevin of Leticia. Now, if we do this at different levels, we find random walks that with different behavior, but as long as the random walk is likely to start in a connected component that's large, its correlation function will decay to 0. If we eventually go to too deep in energy and the random walk is more likely to start in an isolated component, then its correlation function won't decay to 0. It will no longer be ergodic, and we conclude that we must have gone through this topological transition in the landscape. Now, because these models are mean field, we can actually do all these computations with dynamical mean field theory that I think Leticia will describe in future lectures. So we can make explicit predictions for large N behavior of the correlation and response function in these systems. And that's going to be the basis of the results I'll show you next. So how does this work in practice? Well, if you tried this technique with a Brownian random walk, so with just Markovian kicks like Leticia talked about today, then you find that there's an exact correspondence between the dynamics of this constant energy walk and the equilibrium canonical dynamics, as if you had a temperature. And in fact, in these models, we know everything about the equilibrium dynamics. We know that there's a glass transition at a certain temperature, at which ergodicity is broken, and that corresponds to a certain energy density. Now, unfortunately, this energy density is not topologically interesting. We can see this very clearly in a certain model, the so-called two-spin spherical model, which is not a complex landscape at all. It's a convex landscape. It only has 2 symmetrically related minima, and all of the energy level sets of this landscape are just ellipses, just a single ellipse when you take a slice. So the only topological change is at the ground state, where the ellipse vanishes. However, the dynamical transition for equilibrium dynamics in this model is just a typical ellipse. There's nothing topologically special about where you find the ergodicity breaking transition here. So it seems like our scheme has failed. We aren't able to describe where the topology of the landscape changes by a random walk of this kind. But fortunately, we have other kinds of random walks. We can also, as Leticia said earlier, add some activity to our walk, let our walk have a noise which is persistent, and that persistence is not reflected in a damping term, which means that the walk is not described by a canonical equilibrium dynamics, and as you can think of it as a sort of active matter type, a single active particle traversing this constant energy level set. When we do this, as we increase the persistence time of the activity, we find that in the limit of very high persistence, the energy density of the ergodicity breaking transition of the walk approaches asymptotically in this, again, convex two-spin model, which is very simple. It approaches asymptotically the ground state, which is exactly the place in this very simple model where we have a topological transition from having a level set to having no level set. So it seems that we can hope to achieve our goal of understanding where the topology of the landscape changes by using very, very persistent random walks. Now, the more interesting case is complex systems. In complex, in p-spin models with p greater than 2, the landscape is very rugged and complex. And indeed, the same thing happens. When we increase the persistence of the random walk, we find that the energy density of the transition of the ergodicity breaking of the random walk decreases and approaches asymptotically in the pure models, the threshold energy. I remind you, the threshold energy in these pure models is unambiguously the place where the topology must change, because we know in these models, this very sharp division between saddles and minima also gives you a sharp transition in the landscape. So this tells us that even in complex landscapes, very persistent walkers also tell us about this topological breakup. Now, the very interesting question is what happens in the mixed models, where I told you things were ambiguous. Well, here's the cartoon of this picture. Passive random walks confined to a certain set are liable to be trapped by entropic barriers, where active walks can more easily push through. It's the cartoon story. So in the mixed models, what happens? Well, actually, perhaps surprisingly, the energy density at which that appears to be the ergodicity breaking transition energy at infinite persistence appears to approach also the threshold energy in these models. I remind you the threshold energy in these models is defined just by counting the number of saddle points and minima and asking where one is greater than the other. So it's a purely geometric stationary points analysis that sets this energy. And it's not obvious at all to me, for instance, that this would also be the energy at which the typical landscape components break up. But at least in the specific mixed models I study here, oops, go back. The specific mixed models I study here, which you can see have degrees of polynomial that are not so different from each other, the threshold does appear to also be the place at which the typical part of the landscape breaks into a small component. Now, this should maybe get us asking, well, is it true that, based on my heuristic argument earlier, gradient descent does go to the threshold energy in these mixed models? Well, actually, the motivation for the work that I'm describing today was some other work of colleagues of mine that seemed to suggest that gradient descent does not go to the threshold in these models. So I was actually hoping to find a different energy density by this calculation. But it turns out more recent work suggests that with improved integration of gradient descent dynamical mean field theory on these models, suggests that actually for the specific set of models where the two degrees of the polynomial are not so different, the threshold energy is the asymptotic limit of gradient descent after a nasty transient dies out. So it seems that this is fully consistent, that this picture of where the landscape breaks up does match indeed where the gradient descent goes. But this can't always be the story, because we know that if the degree of the polynomials are different enough, there's another regime that's defined here by the fact that this algorithmic limit defined by the overlap gap property goes above the threshold. And here, this means that gradient descent could never hope to reach the threshold, and something qualitative must change about the landscape and the dynamics in this region. And this is the topic of ongoing work. Finally, you might ask, is any of this good in out of mean field? Well, in a certain model called the Random-Lorentz gas, which is a simple model of glasses, of like actual liquid glasses, which involves a tracer in a field of spherical obstacles, you find a similar behavior. Colleagues of mine found, studying this model in the passive form a while ago, a sort of paradox where the dynamical glass transition in this model did not match the density of obstacles at which the percolation transition of the obstacles occurs. And they thought this was sort of strange. But it's not that strange, and when we think back on it, the dynamical glass transition can be caused by entropic barriers. It need not be caused by a topological change like percolation. And indeed, more recent work adding activity to this tracer has shown that as the activity is made larger and larger, the dynamical glass transition is pushed towards the percolation transition, which is fully consistent with the picture I just told about a mean field model. But this is granted in 12 dimensions, but still, you don't really have a dynamical glass transition in this model unless the dimension is quite high. With that, I'd like to conclude. I've talked about how the topology of the constant energy level sets are very important for understanding out of equilibrium dynamics like optimization in random landscapes. And I've shared a new method for trying to quantify that structure. But instead of leaving you on this slide, I'm going to leave this slide up. I have scholarships for students in Sao Paulo, at ICTP Cypher and IFT UNESCO, both for master's students and for joint master's PhD students. So if you're a student who's interested in working on topics like this in mean field disordered systems in Sao Paulo, please look at my website, understand more about my work, and feel free to get in touch. Thank you.
Thank you, Yaron, for your talk. Now we have time for a couple of questions.
Do you think that these results from S sufficiently different that comes from the numerics? Is it believable or not? The numerics, I mean, of the.
Sorry, what do you mean? What different results? Yes. Okay, so I think the state of the DMFT is still inconclusive because it's very hard to integrate with the separation. But the statement I made isn't about their work. The statement I made is the fact that we have an analytic expression that's simple for the E-alg, and we have an analytic expression that's simple for E-threshold. So we can just compare them.
My second question is, for your approach,
Yeah.
how difficult it is to say something about P very different from S?
Yeah, it's also somewhat difficult. My approach is a only one-time DMFT, but it's a one-time DMFT that breaks detailed balance. So you have to use iteration to solve the equations. And I think with a little bit of, let's say, numeric elbow grease, my work could be improved to enter this regime quite easily, I think more easily than the two-time DMFT. But I haven't pursued this yet. At the moment, the 3+5 really pushed what I was doing to the limits of the precision I could pull from it. Because it's hard. It's not only that I have to do the one-time DMFT with iteration, but I want to know not how to describe the decay. I want to know where the decay diverges. So I need to push this all the way to the transition point, which is very costly.
Okay. Thank you.
We have time for another question. Thank you, Yaron, for your talk. Hi, Diego. Now you can share your screen.
Hi, can you hear me?
Yeah, we can hear you.
Okay, perfect.
Please share your screen.
Okay. Now are you watching my screen?
Yeah, we can see your screen, but we have two screens. You are presenting also your next slide.
Okay, so, okay, give me a second. Okay, what about now?
Yeah, now we can see your screen. So
okay.
Our next speaker is Diego Rengifo. He's going to present the talk Fast Thermal Equilibrium using machine learning. Diego, you can continue.
Okay. Okay, thank you very much. Thank you to the organizers to take into account my talk for this nice workshop. Today I'm going to talk about fast thermal equilibration using machine learning. This was part of my PhD in Universidad de los Andes under the supervision of Professor Gabriel Telles. And now I am a guest researcher in the Technical University in Berlin. Okay, so to start, let me set the system of interest during this talk. So we consider a particle that is immersed in a fluid, and we assume that this fluid is in equilibrium at a constant temperature T and with some friction coefficient gamma. And this particle is in interaction with the surrounding particles that belong to the environment. This noise is modeled as usual using the white noise approximation, but also this particle is subject to external potential energy. And this external potential energy depends on some parameter lambda that is externally controlled by some agent. And the idea of this talk is to find this lambda in order that the particles achieve some goal that I'm going to describe in the next few slides. In this regime, when the particle has a bigger mass than the surrounding particles, we can successfully describe the dynamics using the overdamped Langevin equation that is essentially the Newton second law. And this description of the dynamics is called at the trajectory level because we have for every noise realization, we have a particular solution of this equation, but also we have a complementary description of the system using the ensemble description. That is essentially a partial differential equation describing the dynamics of the probability distribution. But we are interested in a very particular solution during this talk for this equation that is essentially the equilibrium state that is defined as a probability distribution at, that satisfies that the time derivative is 0, and we have also a probability current 0, and this leads us to the usual Boltzmann distribution. We are assuming here that the system satisfies these two conditions and the equilibration probability distribution exists. It means that the potential is confined, so the partition function is well defined. But now now that I already described the system of interest, let me talk about the problem statement that I'm going to show you in the next. We start with some initial probability distribution that is characterized by initial potential energy with a parameter lambda I, and we have a final probability distribution and a different potential energy characterized by a parameter lambda F. The idea of this talk is connect these two states at some time TF in the presence of thermal noise and at the same time in the presence of dissipation. But the idea is connect these two states faster than some time scale in the system. So in order to do that, we need the external agent that essentially connected the two states in order to battle this equilibration time. But let me explain in more detail what I mean by equilibration time of the system. Suppose that we have the initial potential energy and we switch this potential energy to the final value. This is essentially a quench protocol. So the system is initially in equilibrium and we see the final value of the parameter. In this moment, the system is in a no equilibrium situation, so it takes some time to achieve the final equilibrium situation with the final potential energy lamp scale. So during this time, we can measure the distance to the target distribution using the Kullbaum-Leibler divergence. So we can define some threshold values. When this distance is lower than this threshold value, we can approximately says that the system is very close to the equilibrium, and we can say that essentially the system is in equilibrium. So using this notion of equilibration time, we have essentially three different regions in the time axis. In usual thermodynamics, we have the quasi-static limit, that is essentially when the transformation is performed very slow, in such a way that the system all the time is very close to the equilibrium situation. We have also an intermediate regime when the protocol time is the same order of the equilibration time. But in this talk, we are interested in the shortcut to adiabaticity theory. That is essentially the control protocol time is much less than the equilibration time of the system. So essentially, the idea is to find this external control agent. How is the dynamics of this lambda t? How is the evolution of this lambda t in order to connect these two states faster than the equilibration time? So the tool that we used to solve this problem was essentially a machine learning approach that now I will discuss in a bit how it works. So let me give you some intuition about this. We start with some parameterization of the parameter of the external control. For example, we can start with a piecewise linear parameterization, and also we can have a neural network parameterization for the control protocol. And we start to tune in the control parameters For example, is the red points in the left-hand side figure. And we start to tuning this parameter in order that some loss function start to decrease. So I'm going to talk in a bit about this loss function. So once the loss function is stabilized and we are confident that the system is very close to the final target distribution, we can safely say that we are found a fast thermal equilibration protocol. So this is essentially a tuning process of parameters in order to achieve some specific goal. But okay, but what I mean by loss function? So essentially is a measure of performance of a machine learning algorithm, and is we can say that is the distance between the simulations respect to the target distribution. So the idea is to minimize this distance. There are several distances in the probability space that we can use, but we found a particular distance that is very suitable for our job, and it's essentially a L-square metric in the Fourier space. So we essentially move the probability distribution from the real space to the Fourier space, and we compute the L-squares metric in the Fourier space. And we did that because the Fourier transformation of the simulation can be interpreted as an average of the complex exponential. And this average can be estimated using the standard estimator for an average. The whole operations that are involved in this average process are differentiable operations. And this is a very important point because this function is differentiable, so means that we can use automatic differentiation to compute the gradient of the loss function and start to exploring the landscape of the loss function in order to find a local minima. And it's essentially the idea to find the fast thermal equilibration protocol. But we can say that half the machine learned. So essentially, we can say the machine has found the fast thermal protocols. Of course, this has to be benchmarked with some analytical results. Unfortunately, I haven't enough time to show you the benchmarked cases, but we did that, and the algorithm find the solution that we want. But now I'm going to show you the main results. So suppose that I have an harmonic oscillator. The control parameters are the stiffness and the center. For this set of parameters that you can see here, for this center value and stiffness, we have an equilibration time of phi. And essentially, we put the time TF, the control operation time, essentially 1/50 faster than the 50 faster than the equilibration time of the system, and we start to train the algorithm. It's important to remark here that we use a combination of the loss function between the loss function that I previously described and also some smoothers in order to find smooth protocols. And here we can see the evolutions of the potential energy of the training protocol. And first, we start with the red line that is essentially the initial potential energy. Then the potential energy starts to move to the objective, but past the final situation, and start to compress at the beginning and decompress at the end of the protocol in order to get the final situation. Of course, the harmonic case is have an analytical solution for fast thermal equilibration protocol, unfortunately, but we reproduce some nice results, for example, for the average work. But the harmonic case is a simple example because the force is linear in the position, but also we solve the problem for more complex potential landscapes. For example, here we have a double well potential, and this double well potential, we deform this using the external protocol until we get an harmonic potential at the end of the protocol. And we did that, and we solved these more complex problems, and this is essentially the results. I have an equilibrium distribution at the beginning with the double well. The idea is to move the left-hand side realization to the right side. So we train this algorithm again with some penalty term. And in this case, for example, we use a machine learning algorithm that is 10 times faster than the equilibration time. So we train this process, and you can see the evolution of the simulations during the training. And this is the potential energy evolution of the training protocol. The physics behind this evolution is essentially, if I want to move the left realization to the right well, essentially the potential energy have to increase in the left-hand side well, and then have to exert some force to this particle to move all the particles to the right-hand well. So this is essentially the thing that I see in the video there. Of course, accelerate the equilibration system has some energy cost, and this also we can have problems with. We can minimize the average work. We have this nice paper of Schmidt and Cipher in 2007, and we reproduce the result of that paper using our approach, using a piecewise linear parametrization, and using also a neural network. But our algorithm is also flexible enough that we can also attack problems with multi-objective situations. For example, in the right-hand side figure, we have the mean work and faster thermalization at the same time. So essentially, we train an algorithm to achieve this multi-objective function. And as you can see in the histogram there is a perfect agreement between the target and the simulations. So essentially, as a summary of this short talk, the take-home message is essentially, it's possible to speed up thermal relaxation using external controls. We can use the machine learning algorithms to find equilibration protocols in the linear and nonlinear problems. And this approximation is quite flexible because I can include constraint, and also I can include more interesting problem as a multi-objective optimization. So yeah, thank you very much for your attention. And now I open for some questions to you. Thank you.
Thank you, Diego. Now we have time for questions.
Hello, Diego. This is Frederick speaking. Many thanks for the talk. So I have a very naive question. So in 2011, there was a PRL by Eric Orrell that followed up some mathematical work in which they established a set of forward and backward, coupled backward and forward equations that allows to solve the problem that you're looking at. And they are valid for arbitrary final time. So what is the problem in taking this final time very short in their equation and solving them? And why is it better to proceed as you proceed?
Okay, you are talking about the paper of, could you remember me the name, please? The authors? It's Aurel, right?
Yeah, right, correct.
Yeah, okay. So yeah, I know the paper. Okay, that is a really good question. Thank you for asking. Yes, this paper essentially, they reduced this problem to a transport problem, but unfortunately, solving the equation that they have are very complex, because at the end they reduce the problem to solve a system of partial differential equations that are coupled. I think that is called the Borger's equations. But unfortunately, it's not so easy to solve this equation. Essentially, my approximation, in my impression, is better because it's more or less easy to implement. We can have many, the dimensionality of the system can be very big. And also we can include constraints to the system, and we can use also in multi-objective optimization. I mean, the thing that they did was with a specific loss I mean, for a specific gold, but here we can have any gold as you want.
Hi, Diego. It's Carlos Viviescas. Thank you for the talk. I want to ask you, with your methods, well, you find a way, let's say a protocol to make the calibration faster. But is this solution unique? And is this the fastest that you can find, or you can go faster? I mean, do an exploration and find several solutions, maybe one of them faster.
Okay, thank you for the question. Yeah, unfortunately, the solution is not unique. You can find different solutions to the essentially to the same problem. The algorithm usually find the same solution, but could be a different solution. Depends on the type of constraint that you have. However, you can find a specific potential energy because we can solve the Fokker-Planck equation in an inverse wave. Essentially, is finding the potential that connect the two probability distribution. In that sense, the potential energy could be unique, but I'm not sure about the control protocol.
We have time for one last question. Another question. So, one question.
Hi, it's Jaren. I have a similar question. I noticed in the example you gave of moving between the anharmonic well to the harmonic well that your protocol had a kind of oscillation in it near the end. I was wondering whether you think this is something fundamental to an optimal trajectory, or it's just one trajectory of many, and that you may be able to find ones that don't have that kind of oscillation in the.
Okay, in the slide that I showing right now.
Yeah, I think one forward. Yeah, here the blue line sort of it oscillates near the end.
Okay. No, that's not. Unfortunately, that's not a universal behavior. That was an interesting feature, but we trained this for some specific constraints. For example, we have a model with the 4-degree coefficient in the polynomial was positive, of course, because the potential energies have to be a confining one. But also we add an additional constraint that is essentially the A3 is less than 0. If we remove this constraint that A3 is less than 0, we have some numerical instabilities in the problem. And sometimes we cannot find a specific solution. So if I remove that constraint, I can find a fast thermal protocol without that kind of oscillation in the potential energy.
All right, thank you.
Thank you, Diego, for your presentation. And this is our last talk of this part of the workshop. We are going to continue at 2 p.m. with with the second tutorial course. So I see you in the afternoon.